Star, lots of smiley faces. Okay, so today I'm going to kind of enter this realm of calculus. So I'm going to go down here, and I'm going to talk about a derivative. Does anybody know what a derivative is? Not at all. How do you know? We all know what assuming does. Nobody? Okay, so let's just say, let's see if we can get you there. The difference quotient is the first step of deriving. Okay, so you can use the difference quotient to derive any function. Okay, so that is equal to the derivative of a function. Okay, so notice I just wrote a new notation for you today. Okay, so this is just like a little slashy line, like a, you know how you would say like something with an S on the end of it? You know, kind of like mines. That little thingy. What is that, apostrophe? We'll call it apostrophe. Okay, so that's what the notation for derivative means. Okay, so if you take the difference quotient, it gives you a derivative. Okay, now I want you to think about the warm-up today and the last problem that I did, and tell me what we were finding. The slope. What's a cooler way of saying slope? What is the slope? Okay, rise over run. It's a rate of change. Okay, so it's a rate of change. So a derivative finds instantaneous rates of change. That is so exciting. Okay, so this like allows us to go past the idea of having a constant rate of change. Okay, so when I say a constant rate of change, give me an example of a function that has a constant rate of change. X, 2x, negative 3x plus 5. Okay, any function that is linear has a constant rate of change. Okay, now tell me in the real world, how often do you think things move at a constant rate? Slim to none, exactly. Very rarely. Okay, so let's do a very basic example, and let's say we are going to drive in a car from this school to, let's just go to MSU. Not far. If I say that we are going to travel at the average rate of 45 miles per hour, does it mean the entire trip I traveled exactly 45 miles an hour the whole way? No, right? That's not going to happen. Okay, so calculus allows us to find instantaneous rates of change. So if we can find an equation to represent my drive from here to MSU, then I can find the instantaneous rate of change of exactly how far or fast I was moving when I turned the corner and took the I-90 exit out on 19th. Okay, which is really cool. This opens the door of so many things. All right, so let's see. Let's do a couple examples. So let's do something quick, and then I'm going to go a little bit deeper, and then I'll let you guys run with this. Okay, so if I was going to find the instantaneous rate of change at x equals 10, anybody want to tell me what the answer is? $16? How'd you get that so fast? 16?
Yeah, that makes sense.
Does that make sense?
Yeah.
You're actually very close. Watch this. Actually, not very close, I lied. What am I doing? What? You don't have to write this down. Because some people might know the answer already. I know the answer already. I canceled it with the other one, sorry. I didn't draw the line. How can I go back to the original and know that the average rate of change for this problem is equal to the instantaneous rate of change at 10? Because it's linear. Oh yeah, right? A linear function always has the exact same rate of change. It was right here the whole time. Okay, so linear functions are super easy to talk about. Okay, it gets a little bit more exciting when we have something like this. Okay, let's say we're looking at x equals 0. Okay, so how would I do this? The limit as, h approaches 0. I plug in x plus h into the x plus 4 minus my function all over h. Ready to FOIL? X plus h cubed. You guys remember Pascal's triangle? It's a good thing I do. So that's what that FOILs into. If you don't believe me, you can FOIL it out for yourself. I used Pascal's triangle. You learned it a while ago. I'm sure you'll never remember it again, but. So, x cubes cancel, 4's cancel. Everything left has an h. You kind of see where this is going every time. Yeah, like every time you use the difference quotient, all of the things that don't have an h in them cancel out. And then I have to pull an h out of everything. And then my h's cancel. Okay, so bottom line of the difference quotient, your second to last step is always going to be canceling out the h. What is the last step? What is the last step? Plugging in 0. H, oh yeah, thank you. Thank you. Plugging 0 into the h's, right? So I would get 3x squared plus 3x times 0 plus 0 squared. So we all agree that that would be 3x squared. Okay, so now how would I find my slope specifically at 0? That was what I asked, right? I plug 0 in. It would be 0. So tell me something very interesting about a slope of 0. Oh, nailed it. Very nice. Say that one more time, Chance. Oh, I did?
Yeah.
Oh, good listening skills then. Okay, so remember, I guess I said that on Monday. Check this out. So if I graph my function, it was what, x cubed plus 4. I'm going to hit a zoom 6 because who knows where I was last time I used this. Okay, so it's going to give us a max or a min, or is this a max or a min? Yeah, it's like where that function middle, like wiggles. Okay, this is called a point of inflection. Point of inflection. Do you see what that means? Okay, so without going too deep into this, it kind of is like where the graph like bends upward. So it was kind of having a downward slope, like a sad face, and then all of a sudden it was a happy face. There you go. Okay, let's do some real world scenarios. Because this is when things get fun. Hold on, let me find my good notes. Where are you? Oh, I don't have any. Perfect. So, what we're going to talk about in this section, or what the book really likes to talk about, is the flight of a falling object. Okay, so for example, if I take a ball and throw it into the air, we can basically talk about many things. We can talk about where exactly it exists at a certain time. We can figure out exactly how fast it's moving at a certain time, and even how fast it's accelerating at a certain time. Okay, so we're going to call this position, velocity, and acceleration of a falling object. So how many people are in physics and have talked about this? Oh, good. Things are gonna like suddenly click. Okay, so I'm gonna start by doing the position. Okay, so I'm gonna use P of t. So t would obviously represent time, right? Okay, so there's basically two ways we can do this. We can do this in feet and we can do this in meters. Okay, so I'm going to give you both because they're going to alternate between this and that. Okay, so who knows if I drop a ball, how fast it goes? Okay, so you said 9.8 meters per second. And then feet is 32, yes? Anybody? Feet per second. You only work in metric? Even in the United States?
Yeah.
That seems weird.
Metric is still better.
Oh.
We use it for science. Just say it.
Oh. Hmm. Oh. Okay. All right, so I'm going to identify some of these things, and maybe some of you physics people can help me. Obviously, time, we said, our t was time, right? In what? What is my unit? Anybody know what V sub O stands for? Velocity. What does the little O thing stand for? Initial. Okay, so it's initial velocity. Mm-hmm. So anybody know what the H sub O stands for? Initial height. Okay, so I'm going to tell you that if we are at some position, does anybody know or want to make an educated guess how I'm going to go from a position to a velocity? What is velocity? It's a rate of change, right? Velocity is a rate of change. Okay, so my V sub t is going to be my derivative of my position. So anybody want to make an educated guess about acceleration? It is. It is the derivative. Whoops, I wrote that wrong. Got excited about derivatives. Bad. So, whoops. Initial velocity. Why do you add initial velocity? Okay, so this would be how fast is it moving? So like, let's say I throw the ball into the air and I want to figure out how fast it's moving after 1 second of time. This is how fast the ball is moving after 1 second. This is my initial velocity, which required movement, right? If I don't have an initial velocity, the ball never went upwards. Not always, because I can drop things and they fall. So by the way, did you know that acceleration is the second derivative of your position? Just a little notation there. Okay, so let's do a scenario. Let's say, example, wait, what?
It says acceleration equals initial velocity equals.
Oh, I forgot to give you the, my bad, 9.8. There you go. How about that?
Well, but there's two apostrophes.
Oh, that means second derivative.
So I just put it.
Yeah, technically you can. That's a good question. I would write 2 of those. Okay, so let's say we're going to, let's throw a baseball, because it's baseball season. Throw baseball. Okay, so let's say a 6-foot player throws with an initial velocity of, let's see, what would you throw a ball at? Yes?
Would you do the arm length?
Um,
Because
if you were gonna get super precise,
when I was-
possibly.
There's never once that I've thrown a baseball that I threw it exactly 6 1. It'd be more like 2.
Oh. Well, let's pretend you're releasing at 6 feet. Just to make this simpler. Okay, with an initial velocity of how fast does somebody throw a ball at? The average guy. 65? The average guy. 60?
70.
That's a huge show. That's
Miles per hour. But let's just pretend for a second that we're dealing with feet per second. Do you see why I changed that? I didn't really want to play the game of converting things. So that's really slow now, right? So 200 feet per second. Huh?
That's one heck of a pitch.
Feet per second? Okay, let's talk about the path of this ball first. Okay, so here's my pitcher, or outfielder, since they're throwing it in the ground. Who knows what's happening exactly? But they throw the ball, and it goes up, and then it goes down. What function did I just draw? A parabola, right? So we're talking about x squared functions. Okay? All right, so let's start with filling out our position. Whoa. Okay, so the first thing that I need to figure out is, am I going to use meters or am I going to use feet? Feet. Okay, so what do I need to use if I'm going to use feet? 32. Okay, so basically all of these 9.8s that you wrote before are going to be 32s, right? Okay, so then it says plus the initial velocity. What was my initial velocity? Does everybody know that initial velocity, or velocity for that matter, can be positive and negative? What's the difference? Huh? Exactly. Okay, so let's not talking about speeding up or slowing down. We're talking about the direction that the ball is moving. Okay, so if I have a positive velocity, the ball is moving upward. If it has a negative velocity, the ball is moving downward. Okay, that's the difference. What's my initial height? 6 feet. Okay, so how am I going to figure this out? How am I going to figure out how fast the ball is moving when it hits the ground? Okay, so I know that I'm going to have to be using which equation to figure out how fast the ball is moving. Which one gives me speed? Okay, well, technically the velocity does. Okay, so we want to find the velocity. How fast is this ball moving? We're going to find the velocity. Okay, so velocity equation is what? Oh, I think I screwed this up before. My bad. I'll go with it. Oh my gosh, I cannot write. I got this. Mm-hmm. Right. Okay, so what do I need to know? Hold on, you guys. I screwed something up. I have to fix it. On my position, this needs to be a 16. So it's not. So when I go back up here, hold on, let me just fix this. This should be a 4.9. And I'll show you, well, I'm not going to show you today why, but so for this one it would be 32 plus this vote. There you go. Beats. There we go. Okay. Okay, so we're talking about this time of the dot, right? Okay, so the only way for me to figure out how fast the ball is moving is to know the time when the ball hits the ground. How can I figure that out? How can I solve for time? Okay, so I'm going to need both of these equations to figure out my time, okay, or my final velocity. This one right here is in terms of time, right? This is position.
What variables do we have?
Time. What variables? Initial velocity, initial height. Okay, so what do we know about the position of the ball when it hits the ground? Okay, exactly what height? 0, right? So this point over here is some t, and the height of it is 0. Okay, so what we can do, I'm going to come down here, I'm going to set my position function equal to 0, whoops, 16 feet squared plus 200 plus 6, and I can solve this. Okay, so we could try and factor this, but I think we should use a calculator and draw it, and just find where we cross the x-axis, right? Assuming we can turn the calculator on. There we go. So 16x squared plus 200 x plus 6. Okay, so let's take a look at that. Oh, negative. Good lord, you guys. Need a negative in there. Because it's upside down, right? I don't see why I don't see it. Negative 16. What's that? Zoom out. Oh, there it is. So it's just super high. So if we hit second trace, number 2, I go till my y is negative. There we go. Okay, so we get 12.5 12.5. Let's go with 12.5. Negative. Okay, so now what would I do? So now you're going to plug 12.5. So obviously I didn't pick a very good real world scenario, right? 200 feet was too big. That'd be sweet though to see. So negative 32 times 12.5 plus 200. Okay, so if you type that in, what would you get? Because it has to all be negative, because it was an upside down parabola, right? Did I get there? 200. Negative, negative, negative. Because it's falling down due to gravity. So feet per second. Right, that would imply that it was going upward. So anything to the left of whatever that maximum was, that's not a very good zoom in, but anything to the left of the max is going up, anything to the right of it would have a positive or a negative velocity. Okay, so I want to take a look at our textbook, and I'm going to give you some more problems to do with the slope and such. Page 762, and I'll write this up there. Let's do those four. Okay, I'm going to have you go 8 through 16. (34 through 40), and I'm writing this down, so I'll put it back up there. Let's do one word problem. That looks cool. So yeah, and 48. Okay, so those are the problems that I want you guys to do.